আচ্ছা আচ্ছা। আমাকে অ্যালাউ করছে না এই জন্য।
Am I audible? So yeah, so hello guys, good evening everyone. So I welcome you all to the third session of Intro to AI Summer School. So I am Sriram. I'm a coordinator at AI Club, IIT Madras. So guys, in the previous two sessions, you were introduced to Intro to Python, I mean, and various libraries like NumPy, Pandas, and Matplotlib, and also object-oriented programming, right? So today is going to be the first session on machine learning, right? So we are going to start our machine learning sessions with regression models. So one thing is, if you guys have any doubts during the session, we'll be giving you chance to unmute and maybe you can ask your doubts. Or otherwise, during the session, if you feel that the doubt needs to be clarified immediately, then you can always text it in the chat and we'll have a team of coordinators who will be helping you out with the doubts, right? So with that, without further delay, uh, I'll start screen sharing. We'll start with the session. Yeah. So is my screen visible?
Yes, it's visible.
Yeah. Okay. Thank you. Fine. So guys, today's session is going to be on regression models. So we'll be discussing linear regression, polynomial regression, and logistic regression in detail. So yeah, so you don't need to worry about what these terms are. It might look complicated, it might sound complicated. It's actually simple. We'll break it down for you, right? So before getting into regression or what regression is, uh, I'll be giving you a brief overview about what exactly machine learning is, right? So what is machine learning? So machine learning, according to Arthur Samuel, is a field of study that gives computers the ability to learn without explicitly being programmed. Right. So Arthur Samuel, he was an American computer scientist. He has done a lot of research work in the domain of artificial intelligence and computer gaming. So checkers is a board game, right? You can see the checkers board on the right of your screen, right? So checkers is a board game, and Samuel was not really great at the task of playing checkers, right? So what did he do? He programmed a computer to play tens and thousands of games against itself, right? And by looking at what positions leads to wins and what positions lead to losses, the program learned to get better and better at the task of playing checkers. So how did that happen? It happened by the computer avoiding getting into bad positions and always trying to get into good positions, right? And as you all know, playing tens and thousands of games is certainly not something which human beings would like to do, right? So eventually what happened was the computer became a better checkers player than Samuel himself. Now, why is this a big deal, right? So what makes this a big deal? The thing is, it was one of the world's first self-learning programs, right? It is true that artificial intelligence and machine learning has seen a lot of developments and advancements in the recent years. But the fact remains that AI or ML is not a sudden innovation. Right? It is a domain which has been developing since the 1960s. For example, this Arthur Samuel, the checkers program, the self-learning program he developed was back in 1960s. Right? So the most important thing over here is in machine learning, you allow the computer to learn without explicitly programming it. Right? So you don't explicitly tell the computer do this, or you don't really give instructions to the computer. You let it figure out itself. Right. So at this point, it's very important to understand the difference between traditional programming and machine learning. Right. So how is machine learning different from traditional programming? So what happens in traditional programming is you start with inputs and you are very clear with the approach that you must be taking in order to get the desired output. Right. So for example, you start with the inputs. The inputs over here are vegetables and chicken. Right. The rules over here is the recipe, right? The recipe to get your chicken dish. So you're very clear with what are the rules or regulation or the instructions that must be followed by the computer to get your desired output. And the computer being an obedient child, it just follows all the instructions that you give and it gives you the output. So in traditional programming, you start with inputs and the rules, and what you get from the computer is the output. But what happens in machine learning? In machine learning, the machine learning algorithm takes some inputs and it takes some desired outputs, right? And it figures out itself what are the rules that you must be following in order to get the desired output, right? So you don't explicitly tell the computer like, look, these are the rules. That's what you do in traditional programming. In traditional programming, you tell the computer you give clear instructions to the computer, right? And that is actually the problem over here is if you're not very sure about the rules or the instruction that you must be giving to the computer, what can happen is you might get a wrong output, right? So one more important thing is most of the problems that we face, right? Most of the problems that we face in real day-to-day life nowadays, they're pretty complicated, right? So we ourselves are not very much sure about the problem-solving approach that we must be taking in order to get the desired output. We only know what are the inputs that we have and what is the desired output. Right? We are not very sure. For example, I can give you an example. The example of autonomous self-driving vehicles, right? So you cannot really, it's not practically possible to hard code all the scenarios and tell the computer or tell your model to take these actions when necessary, right? It's not practically possible. So this is what makes machine learning really powerful and also dangerous at times. So now let's broadly look at the types of machine learning, right? So machine learning can be broadly categorized as supervised, unsupervised, and reinforcement, right? So in supervised machine learning, what happens is the algorithm, it learns from the label data, right? So what do I mean by label data? By label data, what I mean is you have input features, which is denoted by X, and their correct output labels Y. So the goal for the model is nothing but to learn the relationship between the inputs and the correct output labels of your model, right? So it can predict or classify the output for some new data. Now, what about unsupervised learning, right? So in unsupervised learning, you train your model on unlabeled data. In supervised learning, you are training it on labeled data. Labeled data means it's labeled, like the input features are labeled as X. And there are input feature sets, and they have their corresponding output labels as y, right? So that's what you mean by labeled data. But in unsupervised learning, you're training it on unlabeled data. So the goal for the algorithm is to discover the similarities of patterns and sort those data, right? Now talking about reinforcement learning. In reinforcement learning, your machine learning algorithm, it focuses on, it's like a reward and punishing policy, right? So basically, it's like trial and error. You allow your model to, in an environment, to do the actions, and you punish the desired behavior. Sorry, you punish the undesired behavior, and you reward the desired behavior, right? Now, we will look into these classifications of machine learning in detail in the upcoming slides. So first, let's start with supervised learning. So in supervised learning, what you do is you feed your algorithm with labeled data. What do you exactly mean by labeled data? By labeled data, what you mean is you have input feature sets and the correct output labels for those corresponding input features. It's like I give you a question paper with some questions and the solutions, right? So you know what are the questions and you know what are the solutions. So it's like corresponding to the question, there is a solution. So after training, so for example, now you have a data set with pictures of fruits, right? You have pictures of banana, apple, right? And all that. Now, after you train your supervised learning algorithm on a data set with pictures of fruits, right? So what it will do is it will capture these features, interesting features of these fruits, right? For example, banana. Banana is like, you can tell that the color is yellow. It's cylindric, it's like a bent cylinder, it's long. So these are some of the features of banana. What about apple? Apple has some features like it's red in color. It has a depression at the top. It's almost spherical kind of. So these are some of the features of Apple. So what it will do is it will understand these features and it will capture these features from the inputs, and it will try to predict a relationship between these inputs and their output labels, right? So what happens is the trained model examines the fruit shape, color. So the shape, color, these are all the features. Right? There can be many other features as well, like the texture and all that. And it identifies this is the fruit. Okay, this fruit is banana. Okay, this fruit is apple. So this is, I hope you guys got a fair idea about what supervised learning is. Now let's go to unsupervised learning. So in unsupervised learning, you train the algorithm on unlabeled data. So what do you mean by unlabeled data? By unlabeled data, what I mean is I just give you some information. It's just some information. I have not labeled it as this is the inputs or this is the output, nothing. I just give some information. And what you do is you allow the algorithm, you let the algorithm to act on the information and you don't really guide it, right? So without any guidance, you allow the algorithm to capture interesting patterns, interesting features from the information that you have fed it to the machine learning algorithm. So the task of the machine learning algorithm is to group this unsorted information. Since you're not trained the data and you're just giving the information and you're letting the algorithm to figure out the differences, the patterns, or the similarities. That's what you call as unsupervised learning. A good example is Google News. Google News is a good example because what it does is it scouts the internet and it groups all the articles, all the news articles with similar news content or with maybe similar keywords, right? It groups all of them. So it's a very good example of unsupervised learning, right? Now let's go into reinforcement learning. So reinforcement learning is a machine learning algorithm, and it is based on rewarding the desired behaviors and are punishing the undesired ones, right? So basically you allow, there is something called a learning agent, right? So you allow the agent to take actions and learn through trial and error. How do you do that? You reward the desired behaviors and you punish the undesired ones. So there will be some reward given for some behaviors if which is desired, and then there will be some penalties for the undesired behaviors. So eventually what happens is the agent will try to maximize the rewards that it gets and minimize the punishments. Right. So AlphaZero is a chess engine which was developed by DeepMind, and it is a great example of application of reinforcement learning. Now, okay, so this picture I think gives you a fair idea about machine learning and its classification. So machine learning can be broadly classified as supervised, unsupervised, and reinforcement. So as we already discussed, supervised learning is, when you train your model with labeled data, and unsupervised, you're training with unlabeled data. In reinforcement, basically, there is a learning agent. So in an environment, you allow it to do whatever it wants, right? But you reward the desired behaviors and punish the undesired ones, and eventually it will learn how to maximize the reward that it gets and minimize the punishments. Right? Supervised learning can be further classified as classification and regression. Right. So in today's session, we'll be focusing on the regression part. That is, so it's a subclass of supervised learning. So we'll be focusing on regression algorithms. I can give you an example of classification. So for example, tumors, right? The medicine field. So these tumors can be classified as malignant or benign. So there, what you do is you classify the tumor as, okay, it's either cancerous or it's like non-cancerous. So this is a classification problem. So basically, the output is discrete, right? So the output is going to be either cancerous or non-cancerous. So here the output is discrete. So the idea is in classification problem, the output is going to be discrete, and in regression problem, the output is going to be continuous. I'll explain this in detail in the coming slides. So regression. What is regression? So regression is the most, the basic, one of the most basic machine learning algorithm. That's why you call it like the hello world of machine learning algorithms, right? So it's a supervised learning technique that establishes a relationship between the input feature sets and the output labels. The important thing is it tries to map a continuous output function, right? So the continuous valued output is what makes it different from the classification. So in classification, the output was discrete, but in regression problems, the output is going to be a continuous function. Now, a nice example is the housing price prediction, right? So you can see the graph over here. In this graph, you can see some green dots, right? So you can see that these green dots kind of fall all in a parabola. So the best fit curve for this green dots is going to be a parabola. What about the red dots, right? So a straight line seems to be the best fit for this these red dots. So basically, the idea in regression algorithm is to come up with the best curve or the best fit function for a given data set, right? So I'll explain regression in detail. So generally when you get a data set, right? So you split it into training data set and testing data set, right? So the ratio is like 80% training and 20% testing generally. So what you do is you feed the training data set to your algorithm that you can see in this picture. So what you're doing is you have a machine learning algorithm, right? And you have a training set, right? So what you're doing is you're feeding this training data set to your machine learning algorithm, and it learns from this training data set. What do you mean by training data set? The training data set will have input features, right, denoted by X, and the corresponding correct output labels, right? The correct, it's like the correct answers for those questions. I mean, I think that analogy helps, right? So the correct output labels for those corresponding input features. So what our machine learning algorithm does is it learns from the training data set, and then it predicts a relationship between the input features X and the output labels Y, right? So what it gives out is a continuous function, and this continuous function is also called as hypothesis, right? So this you can understand it as a continuous function. So hypothesis, it's also called as hypothesis, or it's also called as model. So what happens is now when you give a new input feature X to the learned model or to the trained model, it will give you a predicted value. The model will give you a predicted value that is denoted by Y hat, right? So this is what regression algorithms generally is. So the idea is you feed in some training data set, your machine learning algorithm learns from the training data set, learns from the input features and the target values, and it outputs a function, right, which you also call as hypothesis. And when you feed in a new input feature X, the output that you get is the predicted value by the model, and you denote it by Y hat. So this notations just note this down because we'll be using it in the upcoming slides as well. All right. So now let's discuss the simplest of all the regression algorithms, that is linear regression, right? So linear regression is basically fitting a straight line to a given data set, right? So what do you mean by this? So as you can see in this graph, right? So you have a data set over here, right? And you want to fit a curve to this data set. So basically, what is the goal of regression algorithm? The goal of regression algorithm is to fit a curve to which closely resembles, which captures all the features of a particular data set. In linear regression, you try to fit a straight line, right? So Y hat is the value predicted by your model. So yeah, so y hat is the value predicted by a model, right? It's also called as hypothesis. We just discussed in the previous slide. So since you're fitting a straight line, the y hat or the hypothesis of your machine learning algorithm is going to be wx plus b. So it's nothing but the slope intercept form, which I'm sure most of you will be familiar with, right? So x refers to the input features. W is nothing but the slope of the line, right? It's also called as the weight. Now, why is it called the weight? So I'll be explaining it when we reach the coming slides, right? So I'll be explaining why you call this as weight. Now it may not really make sense. B is called the y-intercept, right? It's also called as bias. And y hat is the value predicted by your model. So basically, the goal of the linear regression algorithm is to fit a straight line to your data set. Right. For example, you have a housing price prediction, right? So you can see that the y-axis over here, it is price of the house in thousands of dollars. And you have collected a data set, right? So you have collected a data set where you have mapped the inputs, that is size of the house in square feet, to the correct output labels. So what are the input features over here? The input feature is size of the house in square feet. What is the output labels? The output labels is price in thousands of dollars, right? So this crosses that you see over here in the graph, this is the training data set, that the data set that you have collected, right? So what you're going to do is your machine learning algorithm, it will learn from these input features and their output labels, and it will try to come up with a function or with a curve which closely resembles, which captures all the features of this data set, right? So since it's linear regression, we are trying to fit a straight line. Now, one very important thing is, as we saw, the hypothesis is of form wx plus b, right? So you see there are two parameters over here. One is the slope and other is the y-intercept, right? So if I change the slope of this line, I'm going to get a different line. Am I correct? And if I change the y-intercept, again, I'm going to get a different line. So actually speaking, there are many lines that are possible. Like there are many lines that you can fit to this data set. So, now one thing which we should understand is the slope of the line and the y-intercept. These are the two parameters which clearly distinguish a line from the other, right? Now comes the important question. How do we come up with the optimal parameters W and B to get the best fit line for a given data set? Now we saw that if we vary W and B, we get different lines, right? So how do we make sure that the W and B that we have chosen for our model, right, or the W and B that we have in our model is going to be the best fit, right? So how do we do that? So this is one very important question where you need to think about, right? The answer is, see, before you really understand how to go about addressing this issue, you need a quantity to determine how good or how poor your model is, right? So only if you understand how good or how bad your model is doing at the task of predicting output values for some inputs, only then you will be able to determine, okay, should I change my weights and biases? Like, should I change my slope and y-intercept, or what should be done, right? So this brings us to the need of a quantity which determines how good or poor a model is at predicting values for various inputs. Now this quantity, right, this numerical quantity, it's called cost function, right? So what does this cost function do? It quantifies the error between the value predicted by the model and the true output values. So basically the thing is this, the goal of any machine learning algorithm, right, it is definitely to minimize the error, right? So that the model is more accurate, so that the performance of the model is good, right? So we want to minimize the error. So cost function is a quantity, right? So basically it quantifies the error between the value predicted by the model and the true output values. So we know that we are just training our model on some data set, right? So, and the model gives out a prediction as in the form of a continuous function, right? That's what we discussed about regression. Now there will be some error between the true output value and the value predicted, right? Over here, if you see, you can see the line over here, right? So now you have a particular, you suppose, okay, now you take 1,000 square feet. Now this is the value which is being predicted by your model, but it seems like the true value is like around $300,000, right? So, but the value that your model is predicting seems to be $200,000, right? So there is an error. So our aim in regression problem is to minimize the cost function. Not only regression problem, in any machine learning algorithm, like the aim of the machine learning algorithm will be to minimize the cost function. Right. Now, some examples of cost functions have been listed over here. So they are mean square error, mean absolute error, binary cross entropy, categorical cross entropy. Right. The first two cost functions listed over here, they are generally used for regression problems. And the later two, the binary cross entropy and the categorical cross entropy, is generally used for classification problems. Right. So what is mean square error and what is mean absolute error, we will be discussing in the upcoming slides. Right. So one very important thing is the cost function, it has an error term. What is the error term? So we know that the value predicted by our model is denoted by y hat, right? And the the true output value or the output target value is y. So all these cost function, they will be having a term of y hat minus y. So the cost function generally used for linear regression is mean square error. So now we have a problem. So the problem was basically to fit a curve to a given data set, right? Now to determine how good or how poor a model is at this, we are having a quantity named cost function, and our goal is to come up with optimal parameters W and B, right? So that you get the best fit line and you also minimize this cost function. Basically, you minimize the error so that your model is more accurate, right? So now let's look at what mean square error is, right? So we'll be using mean square error for our linear regression problem. So here you can see J. So J stands for the mean square error cost function. Okay, now this looks a bit complicated. I'll break it down for you, so you don't need to worry about that. So what is y hat? Y hat is the value predicted by the model, right? So y hat subscript I is the predicted value by the model for the ith sample. So in a training data set, so now you have a training data set. Now the training data set is going to have m number of training samples. So y hat subscript I is the predicted value for the ith sample, xi in the training data set. So for the ith sample, let's say the predicted value is y hat I. So what you're doing is you are taking the difference between the predicted value by the model and the true output value, right? So y hat minus y. Now, since error can be, so the difference, right? This y hat minus y, this can be positive or negative. So we don't want we actually want the error, right? We don't want the errors to get cancelled out. So to make sure and to ensure that our errors are positive, what we are doing over here is we are just squaring it, right? And after squaring it, you are summing it for all the sample points that you have in your training data set. In your training data set, you're having m number of training samples, right? So you're adding it for all I equals to 1 to m, right? And you're dividing it by m. So basically, you're calculating average of the square of errors. Now, one interesting question is, why do you have a 2 over here, right? So what is this 2? What does this have got to do? So we'll be discussing why this 2 helps. So basically this 2 will help when it comes to calculations and when you implement the algorithm, right? So we'll be getting into the math later, and I'll be explaining why this 2 helps, right? Now, another important thing is for a particular data set, right? So what you do is you're training your machine learning algorithm on a training data set, right? So for a particular data set, this cost function J, it depends only on the parameters W and B, where W is the weight or the slope and B is the y-intercept or bias, right? So in this graph, you can see that this is the model that you have fit. So this is the straight line that you're trying to fit for this data set, right? So you can see that this is the value predicted by your model. Well, this is the true output target value, right? And this difference, so there is an error. So this error, we are trying to quantify this error by the means of the cost function. And here in mean square error, what you're doing is you're taking the difference, squaring it, adding it for all the sample points, and then taking average, right? And you have a 2 here, which I'll be explaining why you have 2 here. So now that we have seen what mean square error is, if we try to plot this mean square error, since I discussed already that mean square error depends only on the 2 parameters W and B. Now, if I try to plot it, what I'll be getting is I'll be getting a 3-dimensional paraboloid surface, right? So the graph over here, it shows you the 3-dimensional paraboloid surface. So one interesting thing is this has only one minima, right? Which is the global minima. And here I have plotted the contours, right? So basically I'm fixing a Z value and I'm just projecting it to the XY plane. That's how I'm getting these contours from this three-dimensional surface, right? So guys, if you remember, the first question that we asked ourselves was how to come up with optimal parameters W and B so that you get a best fit line, right? Because if you change the slope and if you change the y-intercept, you'll be getting different straight lines, and all these straight lines can resemble the data set. But which is the best fit line? How do you go about finding out which W and B will give you the best fit line? So that was the first question. Now, the second question now, which is critical, is now you have decided that for solving the linear regression problem, right, for deciding which line fits your data set the best, you have taken mean square error as your cost function. How do we proceed to minimize it? Right. So we discussed that the goal of any machine learning algorithm is to minimize the mean square error cost function. So how do we proceed to minimize it? Now, the very important idea is the first question that we asked and the second question that we are asking now, they're very interrelated, right? So the first question was how to come up with the correct parameters W and B, right? And the question that now we are asking is how to decrease the cost function. So the goal of machine learning algorithm is to come up with optimal parameters W and B, the weight and the bias, so that your cost function is minimum, right? The answer is optimization, right? So what is optimization? I'm sure many of you would have heard about this term called optimization. So in the context of machine learning, optimization is all about adjusting the parameters. Now, what are the parameters in the linear regression problem at hand now? W and B, right? So the optimization here, so in the context of machine learning, is about adjusting the parameters in the model that minimizes the cost function, right? So as I explained earlier, by minimizing the cost function, you will improve the accuracy and the performance of the model. So there are many optimization algorithms which can be used. So I have listed 3 of them over here. One is gradient descent, other is RMS prop, which stands for root mean square propagation, and ADAM, right? So for finding the optimal parameters W and B, like in the linear regression problem, that minimizes our mean square error, we will be using the gradient descent algorithm, right? So gradient descent is actually the simplest among the optimization algorithms that we have got to discuss. So we will be using gradient descent to find the optimal parameters W and B to minimize the mean square error, because that's the selected cost function, right? For our linear regression problem. So what is gradient descent algorithm? So gradient descent, it is actually an optimization algorithm. So what we do is, so I'll explain gradient descent in simple words first. So here you can see a parabola, right? For example, right? So now suppose I start with a point over here, right? So this is the plot of the cost function with the weight, right? For example, we consider only one. So in our linear regression problem, we have 2 parameters, right? One is the weight and other is the bias. Right. So here we are considering only one parameter for now and only considering the weight. So our plot is going to be a parabola like this. Right. Now, for example, now let's say I start from this point. Right. I start from this point. Right. My goal is to reach the global minimum. So how do I go about this? Right. How do I reach the global minima? Like how do I make it possible for a computer to reach a global minima from this particular point? So what I do is I start from this point. I calculate the slope or the tangent at that point, right? So this slope or the tangent, it gives the direction of steepest ascent at that point. So my goal is to reach the global minimum. So what do? I move in the direction opposite to the steepest ascent, right? See guys, the gradient is nothing but slope in 2 dimensions. Gradient is when it comes to 3 dimensions, right? So now as we are discussing a 2-dimensional case, just take it as slope, right? So slope, since it gives you the direction of steepest ascent, but what we want to do, we want to go in the direction of steepest descent, right? So only then we will be able to converge to this minimum. So what do? We calculate the slope at that point. Then we take some step size called alpha, right? So we move in the opposite direction with a step size alpha. So, okay, now you have reached this point. What do now? You again calculate the slope at that point, right? Now that gives the direction of steepest ascent at that particular point, this new point, right? And again, what do? You move in the opposite direction with a step size alpha. So you keep on doing this iteratively till you reach the global minimum. Once you reach this global minimum, what happens is the slope is going to be 0, right? So basically, you don't really update your weights. I'll explain really how mathematically this is implemented in the coming slides. For now, I hope you got an intuitive understanding of how do we implement gradient descent algorithm, right? So yeah, so I think these two pictures will give you a clear understanding of implementation of gradient descent. So for example, over here, now this is the plot of the three-dimensional plot, like the three-dimensional paraboloid surface that you get when you plot the mean square error as a function of parameters W and B, right? So suppose I start from a random point, right? So basically, what do you mean by start from a random point? I mean that initially I'm just setting my W and B some random value. I don't know what it is, right? Because my goal is to find the optimum values of W and B so that my straight line fits the given data set the best, right? But I don't know what are the true values of W and B, right? So what do? I just randomly set some values. So I just start from some random point. So what do? What I do over here is I find the direction of steepest ascent, right? And I move in the opposite direction. Right, for example, I think in this picture it's even more clear. So suppose I start from this point, I calculate the direction of steepest ascent. I move in the opposite direction with a step size, right? And I again calculate the direction of steepest ascent. I move in the opposite direction with the step size, and I repeat this iteratively. I do still I reach the global minimum, right? So now let's discuss about the mathematical implementation of gradient descent algorithm, right? So here you have a cost function. So this is the cost function that we discussed, right? Mean square error. So it depends on parameters W and B as discussed. So what is it? It's nothing but summation of I equals to 1 to m. Why are you? What is this about? So basically you have m number of data samples in your training data set, right? So for all those m samples, you are computing the difference between the value predicted by your model. So y hat is the value predicted by your model. Y is the true output value or the output target value. So you're computing the difference, you're squaring it because you don't want the sign, you just want you want it to be positive. You don't want positive errors and negative errors to cancel out each other, right? So for that, you're squaring it, you're adding it for all the samples and you're dividing it by m. And you have a 2 over here. And this in this slide, I'll be explaining how this 2 helps, right? So what do you do? Yeah, as I said, you start from some random point, right? So there you compute the gradient, right? So the gradient is nothing but the slope. It gives the direction of the maximum, the steepest ascent, right? So yeah, some of you guys might have studied multivariable calculus. Well, some of you may not be familiar with it. No issues. I will explain to you. I'll explain to you in simple words. So we discussed that the cost function j, it depends upon two parameters, that is the weight and the bias, right? So in that case, so in single variable calculus, suppose you have a function like h square, right? So when you differentiate or when you find the slope, when you find the derivative, you get 2h, right? So but when you have more than one variables, what you do is there is a concept called partial derivatives. So basically what you do is you change one parameter at a time. You don't change both of them, right? So this you read this as dou j by dou w. So now since cost function depends upon two parameters w and b, here you're keeping the parameter b constant, right? And you're like, okay, now let me vary w. How much is the cost function gonna vary? So that's what dou j by dou w stands. So dou j by dou w is nothing but the change in cost function when you change the parameter w and keeping b constant, right? So by chain rule, what happens is when you have y hat minus y the whole square, right? So when you take derivative, this 2 over here and this 2 in the denominator, they get cancelled out. This is the reason why you have this 2 over here. I hope it's clear, right? So when you take the derivative or when you take the partial derivative by chain rule, this 2 in the exponent and the 2 in the denominator gets cancelled out. So you get 1 by m summation y hat minus y, right? And now it's time to differentiate, right? You're differentiating with respect to w, right? So what is the coefficient of w over here? H. So that's how you get the h over here, right? And similarly, if you compute the partial derivative of the cost function with respect to b, right? You get, okay, this 2 and this 2 gets cancelled. So you get 1 by m summation y hat minus y. And now it's time to differentiate y hat. So what is the coefficient of b? 1, right? So you get a 1 over here and you don't have h over here. So now you have computed the gradient at the current point. Now what do? You update the weights and biases, right? So weight and the bias is the parameters that you will be updating at each step. And after a point, right, you will converge the global minima, right? So what happens at that point is this gradients, they become 0. So basically no updation of weights and bias takes place once you converge to the global minima. So here, when you update the weight, so W equals to W minus alpha, dou J by dou W. Now, why is there a minus over here? Because we are moving the direction opposite to the gradient. Gradient or the slope, it gives the direction of steepest ascent. But our intention or our need is to move in the opposite direction. So you have a minus over here. The steps is that you are taking, right, as we discussed before, it's called alpha, right? So W equals to W minus alpha dou J by dou W. So you updated the weight and simultaneously you update the bias, right? So B equals to B minus alpha dou J by dou B. Now, after you update weight and the bias simultaneously, now you are at a new point, right? So what I have done, what these two expressions over here, it's nothing but just rewriting this dou J by dou W, just writing it again over here for weight, and dou J by dou B, this expression, I'm splitting it over here, nothing more, right? So these steps are sequentially repeated till you achieve convergence. Once convergence is achieved, what happens is the slope becomes 0. That is the gradient, it becomes 0. So basically, after you reach the global minima, there will be no updation of weights and bias, right? So guys, now I think it's time for quiz. So maybe you guys can scan this QR code and try out this question. I hope you guys scan the QR code. Okay, fine. So most of you have. So guys, one more important thing I forgot to mention, sorry. This is a multiple correct. Right. So that's, I'm sorry, I forgot to mention that this is a multiple correct question. So more than one options are correct. Yeah. So guys, yeah, your answers are correct. That means, so yeah, so these two options, the first two options. So the reason is this: mean square error is mathematically easy to compute. So this is not the most important reason. The most important reason is that you have a single minima. Okay, the poll seems like 69% of you tell that it's easy to compute. Okay, interesting. Okay, I'll explain the answer for this question in detail. Right. So yeah, so guys, the answer to the question is, so there are two options correct. So the first option, the most important reason is that mean square error, it just has a single minima, which is the global minima, right? So why is that a reason for choosing mean square error as the cost function? So now you can see two plots over here, right? One over the left and one on the right. Now this plot, the plot on the left, this is for the mean square error cost function as a function of parameters W and B. Now this over here, the graph over here, it is the plot of some other cost function which has more than one minimas. right? So in this graph, now I told you that initially we'll be assigning random values for the weight and the bias, right? So you'll start from some random point and then you'll implement the gradient descent algorithm and then you will converge to the global minima. So this is what happens. So in this first plot, right, no matter where you start, when you implement gradient descent algorithm, when you update the weights and the bias, you will eventually convert to one minima, which is definitely the global minima, because there's only one minima, right? And that's the global minima. But over here, it's not necessary that you converge to the global minima. I hope it's evident, because see, suppose you start from this point, right? You update the weights and bias, you are at a new point and you implement gradient descent. You implement gradient descent algorithm and you are finally converging to this minima, right? But over here, if you start from this point, right? If you start from some other point, you're converging into some other minima. So how do you make sure if you use some other cost function? The problem is you will not, if you're implementing gradient descent algorithm, you will not really be sure that the minima that you have converged is it the global minima or not, because there are multiple minimas. So there is a chance that you might have converged to some minima which is not the global minima, right? So that is the most important reason. And also, yes, it is indeed true that it's mathematically easy to compute because of its simple quadratic nature, right? So y hat minus y the whole square, and you sum it for all the points, and then so that's easy to compute. So that is also equally correct answer. So those two options are correct. And the other option, the other two options are, I'll just take the other two options as well and explain that as well. Yeah. So the first option is mean square error is mathematically easy to compute due to its quadratic nature. So yeah, most of you have voted for that. Yes, that is correct. So the computation power required will be less, right? Because of its simple quadratic nature. Now, second option is, yeah, the mean square error as the plot as a function of parameters w and b, it has a single minima, which is the global minima. This is the most important reason for using mean square error while implementing gradient descent algorithm, because the minima that you converge to, you are sure that it's the global minima. Yeah, the other option is using mean square error as the cost function helps in achieving faster convergence. This is actually not true, because how fast you achieve convergence or how fast you converge to the global minima is determined by the parameter or the step size that you are taking, right? The alpha, that was the step size that you were taking to converge to the minima. So how fast you converge, it depends on alpha. So not really on the cost function. So the plot of mean square error is bounded. So this itself false because we saw that the plot was unbounded, right? So I think the first two options, I mean A and C, the first and third options of the poll, they were correct. Yeah. So so we discussed about a little before, we just discussed about the step size alpha, right? The step size that you take for convergence. So what is alpha? Alpha is a hyperparameter. Now, first question is, what is hyperparameter? Right. So hyperparameter is a quantity or is a quantity that you specify while you implement. It's actually dependent on the user when he or she implements the machine learning algorithm. Right. So it's something user specified. So it is used in optimization algorithms that refer to the rate at which the model learns. So in the context of gradient descent, it is actually the step size that you take to converge to the global minima. Right. Now, one thing is, if your step size, that is alpha, is very small, right? What happens is it is going to take a lot of time for you to converge to the global minima, because because you will be just updating very slowly. So a lot of computational power and effort will be taken in order to converge to the minima. But if you have very large alpha, right? So this is the parameter W, right? So you have very large alpha. So suppose suppose you start from one point and you compute the gradient and implement the gradient descent algorithm. And when you update the weights, it might happen that you overshoot the minima. So if you overshoot the minima, again, it's again, so you'll have this zigzag motion. Finally, after a lot of time, you will be able to converge. So that is also undesirable. So a very small alpha can get you into trouble because it's going to take a lot of time, a lot of computational effort required to converge. And a high alpha is also undesirable. So this brings us to the need of having an optimal alpha, right? which is not really high, which is also not really low, so that you can converge faster, right? So how do you make sure that the learning rate alpha chosen, right, while implementing an optimization algorithm is optimal? So what you do is you plot the cost function with the number of iterations. So when you plot cost functions with number of iterations, so we discussed that the goal of the machine learning algorithm is to minimize the cost function, right? Now this plot is actually called learning curve, right? When you plot cost function with number of iterations. So at some point, if you see that cost function is increasing, right, it means clearly that you're overshooting the minima. So if you see that the cost function is increasing after single iteration, it means that the chosen alpha is high and you don't need such a high alpha. So this is one way in which you can choose the optimal learning rate alpha so that you achieve faster convergence, right? So guys, till now, the linear regression that we discussed, right? The hypothesis was y hat equals to wh plus b. So basically, we are considering only one input feature h. Now, for example, even if you take the housing price prediction, right? So the plot that we showed before, it was just nothing but it was just the size of the house as the input, right? Size of the house in square feet as the input, and the price of the house in thousands of dollars as the output label, right? So, but the truth is that the price of the house it's based on a lot of other factors as well, right? Not just on the size of the house. So what is multiple variable linear regression? So it's nothing but an extension of linear regression, right? The only thing is instead of one input feature h, you have multiple variables, right? h1, h2 goes on till hn. So you can take into n input features into consideration in your model. Earlier, when you were implementing single variable linear regression, you were able to include only one input feature, whereas over here you're able to take into account n input features. So y hat is the value predicted by a model is w0 plus w1 h1, w2 h2 goes on to wn hn. Now w, like the w0, w1 and goes on to wn. So these w is called weight. They are called weights. Now you will probably get an understanding why we call this w as weight, because it clearly determines how important or what is the significance of each input feature. Right. So multiple variable linear regression, it helps in accommodating multiple input features, right? Unlike single variable linear regression. So it's one of the most widely used machine learning algorithms even today, right? So yeah, now my friend Anish will be taking the code implementation of the linear regression algorithm.
Hi everyone, I'm Anish and I'll be covering the implementation of linear regression. So before we start with the linear regression, we need a data set on which we can perform the linear regression. So that's what we'll be doing. First, we need to import NumPy and Pandas as it's pretty important. And then we'll be setting the random seed for reproducibility. So I guess this would be the first new concept. So what does this mean? Basically, this standardizes the random values which are generated. Basically, like how many ever times I run it, I'm going to get the same set of random values. You take this code and run it on your Collab notebook, you'll be getting the same set of random features. However, if I remove this single line of code, every single time I run the code, I'm going to be getting different feature values. So that is the need for setting up the random seed. I think someone has asked it in the chat, so I'll just repeat it once. It makes sure that the same feature values are generated. If I just make it random, then I'll be getting different values every time I run the code. So moving on, now I'm going to have like a data set of 200 random values. This number can be anything. I'm just taking 200 for convenience. So I'm going to get 200 random values of X. Now I'll also generate noise, 200 values of noise. So let's say I don't have noise, I'll be getting a single straight line. And we don't want that. We want it to be like real world like data set. And in real world, there's always noise because of some error or some disturbance. Okay, one more question. Why is 42 used? Well, 42 is like, I mean, you can put any number, it doesn't matter. It's just like, I've taken 42 and maybe it's used often, not sure about that. So yeah, coming back to noise is basically like to prevent the data from just being a straight line. And noise, like we'll just come to a visual representation of this in some time. I'm going to be predefining the weight and bias early on. And later we'll see if the model is going to learn this value. I'm defining 3 as the weight and 5 as the bias and noise. I'll be saving it as a data frame and even as a CSV file so that if I need it later on, I can use it. This is my data set. On plotting the data set, I can see that the points are like this. So this is where the noise has come in. Let's say noise was not there, it would all be a straight line. So this is a better example for us to implement linear regression on. Yeah, we do need to choose equal quantities of values and noise because like it's like for each data point, there's some corresponding noise which is randomly generated. Without noise, it'll just be a single straight line. So a quick recap on what Sriram covered earlier. This is our cost function for linear regression. It's 1 by 2m, sigma I is equal to 1, 2m, y predicted minus y predicted minus actual y whole squared. So y predicted is nothing but wx plus b. As you know, it's a linear regression. So when we differentiate it partially with respect to w, we get this. And when we do it with respect to b, we get this. It's easy to understand. It's like this partial differentiation. So we'll move on to linear regression from scratch. So sometime earlier, someone had asked about hyperparameters. So in this code, these are the hyperparameters, number of iterations and learning rate. Why are they hyperparameters? Because I'm defining it right now and it can be anything. But of course, like if you just put it as anything, you won't really get a good accuracy at the end. The thing about learning rate is if it is too fast, you might miss the minima and you might overshoot, which is not good for us. And if it is too slow, it will take too much time to reach the minima, which is also not good for us. So we need to hit that sweet spot in the middle. And then there's number of iterations. If we have too many iterations, it will do something called overfitting, and overfitting is also bad. Overfitting is when it performs exceptionally well on the training data, but performs poorly on the test data. This is because of too many iterations. So yeah, these two are our hyperparameters. So now we will initialize variables w and b. W is nothing but the weight and b is bias. As you can see, like the actual value of w was 3 and b is 5, but we're just initializing it as 0. Our goal at the end of this code is the model should itself predict the values of w and b. Next, we have 3 lists: history, cost, w hist, and b hist. And all these three, like the main intention is just to plot graphs later on. It's not directly related to the algorithm. So let's get started with the main algorithm. For I in range number of iterations, this basically means that the iterations is going to be like 100. So it's going to go through the data 100 times. I guess you'll be able to recognize this line. This is the standard linear regression line. And now I hope you remember the cost function. We'll just be writing y expected minus y pred as error, as you can see here. So the cost function eventually becomes 0.5 into np.mean error square. So now we will have to find dj by dw and dj by db. Like it's written dw and db here, but then it's like that's just for short form kind of. It's dj by dw and dj by db. And you can see that these two will kind of, it's corresponding to what's written here. So like nothing surprising. Now, of course, we'll have to update the weights and biases in every iteration. And as you know, this is how it's done. W is equal to W minus learning rate into DW. The learning rate comes into picture here. Similarly, for bias, it's B is equal to B minus LR into DB. I hope it's clear. So this is essentially the end of the loop. Like again, history, cost, W hist, B hist. It's just a list to later on plot things. Like that will help us improve our understanding. So I've already done this thing, and let's see what W and B have come. So it's predicting the weight to be 2.81 and the bias to be 5.15 at the end of 100 iterations. So if you remember from earlier, we had set the weight as 3 and bias as 5. So it's pretty close, 2.8 and 5.15. Basically, the like slight deviation is because of the noise. Okay, I'll repeat dW and dB. dW and dB is just the differentiation. It's the partial differentiation of cost with respect to weight and bias respectively. I hope it's clear. And one more person has asked, if you use a large alpha, we can do it easily, right? Large alpha is basically large learning rate, I'm assuming. And the problem is, if you use a large learning rate, you might overshoot the global minimum. And you might, it's like a curve, right? So you might start going in the opposite direction, which is not good. So this essentially was the algorithm from scratch. It's not really that complicated. So we'll just plot cost now. And this is how the cost varies over 100 iterations. If you can see, like approximately till the 20th iteration, it kind of reduces steeply, and then it kind of just saturates over time. So what this means is I'm going to get a similar kind of result, even if I stop the number of iterations as 20. And yeah, that might have been a better option to prevent overfitting. But yeah, this is just an example, so it doesn't matter much. So now we'll look how the graph looks after predicting the weight as 2.8 and bias as 5.15. So now you can see the line is a pretty good fit. It's like it's passing through the middle of the entire data, and it's on an average, it's performing a good. It's going to have a good accuracy. Let's say if I had a test set. So let's just visualize this. This part of code, like it's not really used often. This is just to show how the line varies over time. I'll just start it from the starting. So basically, you can see it just rises up slowly. That's because the weights are being updated. And one more thing, if you see, like this entire like animation is of 10 seconds and it has a lot of frames. If you notice one thing keenly, you will see that for the first 2 seconds, it kind of changes a lot and then it just kind of stagnates. This is again like it's a reflection of the cost function if you see clearly. Here also in the first 20 iterations, it goes quickly down and then it kind of stagnates. And that's what is reflected over here in this animation. I'll just play it one last time for you to see. So like we won't know beforehand how many iterations should be there. Like you can take a guess and then you can always plot these graphs and then decide what is the best hyperparameter. So that's the deal with hyperparameters. You will have to choose the best value. So now we'll be doing the same linear regression, but with a predefined model. You'll see it's much easier this way. So this is the same data set that I saved earlier in the code. Now I'm just separating the X and Y. If you can see, like this will basically return all the rows and column 0, which is the target. Sorry, not target, it's the feature column, while Y will have all rows that are in the target column. We need to reshape X here. It's very important. This is because when we are fitting it into a model that we're using like sklearn, what this does is it kind of changes the shape of X to make sure there's no problem while using it in the model. So now that we're using sklearn, it's pretty easy. We just need to do dot fit and the model is trained. And once it's trained, we just use more predefined functions such as model.intercept and model.coef to find the intercept, which is the bias, and slope, which is the weight respectively. And we've gotten the intercept and slope as 5.1 and 2.9, which is also similar to what we defined earlier. It was 5 and 3. And according to the from scratch model also, we had gotten similar amount of weight and bias. So it's a pretty good prediction. So like sklearn, basically I'm just like importing the model. I don't need to do it from scratch. It makes it much easier. And this is what is usually done if you use it. You don't always code stuff from scratch. It's a Python library, yeah. And why is reshape used? Reshape is used to prevent any errors when you're fitting it. Like you can, like while you're running, you can just try to see the difference between X and X dot reshape later on. It kind of like, the thing is, it has to take, within the function, there are a lot of things happening. It goes in batches, and there's also like, you need to arrange it in a way. So it makes sure like there's no error in the dimensions. So that's the need of it. I hope that's clear. And now we have the line, which is pretty similar to the previous one, but slightly better fitting because you can see the weight and intercept is closer to what it was. Okay, so now we will be trying with a more complicated data set. Till now, whatever we saw, there's like one X column and we're just predicting the Y. But now we're going to have a lot of feature columns, 8 to be exact, or maybe 9. But yeah, let's start. Now we'll be needing even more stuff, imports basically. We need train test split, we need linear regression, we need mean squared error. Pandas and NumPy was already imported. We don't need to import it again, but I've just showed it in case anyone forgot. We'll also be using two libraries, label encoder and min-max scaler. We'll see why this is used. It will come into play soon. So this is how the data looks like. This is a housing data set and it's pretty popular with linear regression. So like straight up, as you can see this data, you will realize like there are two major problems. The first one is that okay, I'm just making it clear, median house value is the target column and the rest of it is features. So the first issue is that ocean proximity doesn't have integer values in its rows. It has like stuff like nearby and inland. So we'll have to change this into numeric values, and this is where label encoder comes. Also, you might have noticed one thing, like some columns have like really huge values, while some columns are really small. Like you see population, it's 2,000, 1,000, and 500, 800. But then median income is usually 875. This basically leads to domination of some columns over the other. This is where min-max scaler comes. Min-max scaler ensures that all the values are between 0 to 1, basically. We'll come into the technicalities of this later. First, we have a quick Slido coming up. So you guys can scan this and just try out. It's pretty intuitive. We'll get to the implementation after this question. You can scan and try this. I'll just wait for like maybe a minute or two for you guys to attempt it, and then I'll show the results. So yeah, I'll just show the results now. So yeah, I've gotten a lot of responses as 8, some 64. Well, the correct answer is 8 only. So basically, there is going to be one weight per column, and bias is going to be only 1. So it's just 8 into 1, which is 8. And I remember initially someone had asked in the chat, why is it called weight? Why is slope called as weight? So in one way, you can see, the weight decides how important each column is. So yeah, that might be one of the possible reasons, but that's all just nomenclature. So yeah, getting back to this question, the answer is 8 because there are 8 weights and 1 bias. There's like 1 weight for each column and 1 bias overall. So yeah, let's get back to the code implementation. That's the end of the Slido. So someone had asked, why can't we use one-hot encoding over label encoding? Well, one-hot encoding usually gives a list, and label encoding is usually more useful here. We'll see why. So yeah, we have the data ready over here. So we're just extracting the feature and the target. So X is going to be every column except for the last column. That's why this code is here, semicolon -1 dot reshape again. And Y is going to be the 8th column. 8th column was the median house value. I could have also written -2 because it's the second last column, which is the target. So what label encoder does is it basically gives like in this, there are 3 possible values in ocean proximity. You can only see 2 here, but there is one more. And what it does is it basically gives it an index, basically 1, 2, and 3. And this is corresponding to the number of times it occurs. So that is kind of useful. One-hot encoding usually gives a list, and label encoding seems more apt over here. And then we'll be using min-max scaler. Min-max scaler, as I said earlier, will convert all data from between 0 to 1 so that no column dominates over the other. So this is what happens in the when you use min-max scaler. df is basically, you can say it's the value of the row, and df.minimum is the lowest value in that entire column, and df.max is the highest value in the entire column. So it's a simple operation, and this makes sure that the values are normalized. We can see the new data set how it is. So this is how it is. I mean, you can use any scalar. I'm just like, this is just an example. And it's a pretty good scalar. I'm getting a pretty good, I'm getting a really low error with this. So it has worked out for me. So as you can see, firstly, ocean proximity doesn't have strings. It has numbers, and everything is between 0 to 1. Initially, some columns had like really high values, and that's not the case right now. And again, we'll be doing it with sklearn, so we don't need to do it by scratch. So let's see what we're going to do. We are filling all the, like, it's mostly the same imports. It's like, it's not needed to do it again. This is just to show what is going to be used. Anyways, we're first going to fill all the null values with 0. This prevents any issues when you fit it. Basically, null values, it's usually NaN, which is not a number, which is not suitable when you're using linear regression. We'll just replace it with 0. And we are going to, like, the x and y is defined again. So now we imported the train test split earlier, so we're finally getting to use it. X is the feature columns and Y is the target. It basically splits it into test data set and training data set. And I've defined the test size as 0.2. So 0.2. So this makes sure like 20% of it is test, while 80% is train. Again, there's a random state to make sure it's like randomly distributed. So now we have X train, X test, Y train, and Y test ready. So we are ready to fit. We are just defining the model as linear regression. We have already imported it, so it's just a line. So model.fit basically trains the model. We don't need to do anything else. And now if we do y underscore predict is equal to model.predict x underscore test, we get the predicted values as well. So, and there's also a like direct function for finding the mean squared error if we just input the y test and y pred. So we really don't need to do anything on our own. And at the end, this time we are not predicting weights and biases. We'll just directly calculate the mean squared error since we have a test data set with us. And the mean squared error is 0.02, which is pretty low, which means like it's a good model and it's predicting the median housing value pretty well. So if you have any other questions, you can ask me, or we'll move on to, I think it's polynomial regression. So yeah, I think we can start with polynomial regression.
So this is my screen visible. This is my audible. Hello.
You are audible.
Yeah, fine. So guys, any doubts regarding linear regression which you want to ask, you can raise your hands now, and you will be unmuted, and you can ask the doubt regarding linear regression, like whatever has been discussed till now. Okay. So yeah, so now let's start with polynomial regression. Right. So polynomial regression, it is a regression algorithm that models the relationship between the output y hat and the input features as nth degree polynomial. So basically the thing is the hypothesis of the regression algorithm is going to be an nth degree polynomial, right? That's going to be w0 plus w1x plus w2x squared goes on to wn x power n. Now, this polynomial regression can actually be considered as a special case of multiple variable regression. So in multiple variable regression, it was w0 plus w1 x1, w2 x2, and goes on to wn xn, right? So basically, you were accommodating n independent features into your model. Now here, instead of accommodating n independent features, you are just accommodating the higher orders of the same input feature x, right? So it's like w1x, and then you go with the x square, x cube, and goes on to xn. Now, how does polynomial regression help? See, most of the times what happens is the data set that we'll be having, like the curve that we have, like the data set on which you have to fit a curve, it's mostly not going to be non-linear, right? So fitting a straight line is not necessary. Like most of the times, it's probably like not going to be the best idea, or it's not going to be the best fit for the data set. So this brings us the necessity to fit a curve, right, of like a polynomial of a higher order, right? So you can, but you can also visualize linear regression. You can understand linear regression as a special case of polynomial regression, right? So if n equals to 1, then y hat is going to be w0 plus w1h. So that's a special case of, so linear regression becomes a special case of polynomial regression when degree is equal to 1, right? So you can see the housing price prediction. Now here you can see the data set, it's actually not linear, right? So maybe a curve like this would be a better fit to this data set than a straight line, right? Now, for example, yeah, over here. Now this data set, now these data points seem to fall on a parabola, right? But if you try to fit a straight line, this is what you get. And here the straight line is not clearly capturing all the features of the data set, right? But if you try to fit a polynomial to this data set, see it is probably the best. So this polynomial, like the b0 plus b1x plus b2x square, it's the best fit for this given data set, right? So basically the thing is linear regression, it fails in capturing the nonlinear relationships in the data, right? Which polynomial regression can do, right? So polynomial regression helps in bringing more features. What do I mean by more features? More features means the higher orders of the input features into consideration, right? So for example, over here, if you have the polynomial degree 1, so basically this is, so if you have the degree as 1, it's going to be w0 plus w1x, right? So basically it's a straight line. So you're trying to fit a straight line to this data set, and you can see that it's not properly fitting the data, right? So you call it underfit. Now you add the quadratic feature, cubic feature, and finally you get you bring in degree 4. So what happens if you try to fit a curve of degree 4 is, yeah, it closely resembles the data set, right? So it is able to capture the necessary features and the important features of this data set. But what happens if you increase the degree further, right? For example, if you have a degree 20, so it looks like this, right? The plot, it tries to pass through all the input data points. So when you try to bring in this new idea of polynomial regression, now you encounter some new problems, right? So these problems are overfitting and underfitting. So if you observe the leftmost graph, right? So here you can see that this is the data set, and when you try to fit a straight line, this is what you get. Now you can see clearly that straight line is definitely not the best fit for this data, right? Now, if you try to add a quadratic feature, right? So now your hypothesis is w0 plus w1x plus w2x squared. So now you have a quadratic feature as well. So now when you try to add a quadratic feature, you get a good fit or maybe the best fit for this given data set, right? So, but if you have too many features, right? So if you increase the degree to some 10 or 20, what happens is your model, it will be fitting this training data set very well, right? It will be trying to pass through all these data points in this training data set. But this has some problems, right? So when overfitting takes place, so when your model tries to pass through all the points and when the degree is generally very high, you call the situation to be overfitting. Now this curve is an overfitted curve, right? It fits very well to the training data. It fits probably too well to the training data set. This curve, it's underfitted, right? Because it is no way capturing the important features of the data set. So the problem with overfitting is that your model is going to be very sensitive to outliers, right? So there is a, so, and you can also see that the linear regression, if you implement linear regression, you try to fit a straight line. Straight line is actually not able to capture the features. So both underfitting and overfitting, both are undesirable, right? So I'll explain in detail what underfitting and overfitting is. So underfitting occurs when the model that you're trying to fit is too simple to capture the important features in the data. Right. In the previous example, you could see that the quadratic feature was able to, the parabola was able to fit, or when you introduce a quadratic feature, the fit was it was neatly fitting the data set. So before that, it was a very poor fit. Right. So when you try to implement a simple model like linear regression over a data set which is more complex, right? So in those cases, you encounter underfitting, right? So what is overfitting? Overfitting occurs when the model becomes too complex, right? So you're actually not only capturing the necessary pattern or the necessary information, but you'll also capture the noise in the data, which is undesirable, right? So this generally happens when the degree of the polynomial is high. As you can see, if the degree of the polynomial is high, it will try to pass through all the training data points. So this is also undesirable. So to understand underfitting and overfitting better, let's introduce two new important concepts. They're called bias and variance. Right. So first, let's understand what bias is. Bias is the error that arises when the model chosen or the algorithm is too simple to handle the complexity. Right. For example, the data that you have over here, it is not linear, clearly. And now here you are trying to fit a straight line. So the model that you're trying to fit, it is simple, but the data set, it's actually complex. So in this situation, you tell that this model has high bias. What does that mean? It is too simple and it is not able to capture the important features. And high bias leads to underfitting. Right. When you have high bias, it means the model is too simple, and you need a much more complicated model which will fit the data set better. And because you have a simple model and it's not able to capture the features, underfitting takes place. Right. For example, as you see when you try to fit a straight line to a nonlinear data set. Now let's discuss variance. So variance, it refers to the error that occurs when you try to really complicate your model, right? So when you include so many features, and when you try to incorporate so many features in the data set, so unknowingly you also take the noise into consideration, and in that case, your model is said to have high variance. Variance basically it refers to like how sensitive your model is to the fluctuations in the training data, right? Suppose I change this training data a little bit, right? The output function of the model is going to be totally different. So high variance means that the model is trying to pass through all the training data points. So what is actually the problem if it tries to pass through all the training data points? The problem is when it comes to testing, it will do very poorly. Ultimately, our goal is to come up with a model which should be good at testing, right? So that you train it, and finally, when you give a new input X, the output predicted by your model should be close to the true output value, right? And if there is a big error in the testing part, then the model is actually useless. So high variance is also undesirable. So guys, so this is now it's quiz time again. So you can scan this QR and answer the poll. Okay, wait, I'll share the QR for some more time. Yeah, it's yeah, so yeah, all of you, I think most of you have got the correct answer. So low bias and low variance, the ideal scenario, right? I'll explain in detail why low bias and low variance will help. Right. So we saw that high bias and low variance, it leads to underfitting. What do you mean by high bias? Your model is too simple and it's not able to accommodate all the features. And low variance means, again, the model is again too simple. So in these cases, it will lead to underfitting. When you have high variance and low bias, that means that your model is really more complex than required. So it leads to overfitting. So what is the ideal scenario? The ideal scenario is you minimize both bias and variance, right? So only in that case, the model will be successful in capturing the features and patterns of the data. So you will be, in that case, if you have low bias and low variance, you will be avoiding both overfitting and underfitting. So now but there is one more issue over here. The issue is bias and variance. These are two opposite opposite parameters, right? So if you have high bias, then you have low variance generally, and generally when you have high variance, you have low bias. So how do you go about having low bias and low variance? So low bias and low variance is actually the ideal scenario, right? So practically what happens is you get moderate bias and moderate variance, and then you'll be satisfied with that. And because these are two opposite parameters and there's a tussle between them. So this brings us to the necessity of optimizing these two parameters, bias and variance, right? So optimizing bias and variance. So how do you go about this, right? So what you do is you plot the cost function for every degree of x, right? So when you plot the cost function for every degree of x in the testing data, you can find the minima. So the minima is found as the optimal order where in order to balance the bias and variance. So basically, where you are getting the order n of the polynomial for which the cost function is minimum, that is going to be the optimal order of the polynomial in order to balance bias and variance, right? So in this graph, you can see that where you have underfitting, right? The training error is also high because for example, the straight line on a nonlinear data, it is not fitting to the data set very nicely. So the training error is also high, and testing error is also going to be high. But in the case of overfitting, the training error will drastically decrease, but the testing error increases. So that is also undesirable. So the best fit will be the one which kind of optimize both bias and variance. How do you do that? You just plot the cost function for every degree of x, and the degree of x for which the cost function is minimum, that will be the optimum degree that you can include, that for which you will be implementing your polynomial regression model, right? So guys, this is the QR for attendance. So you can scan it now. We'll also be displaying this at the end of the session. So yeah, for now you can scan this QR code. I'll just wait for 15 seconds. Yeah. So now let's go to the code implementation of polynomial regression.
Sriram, I think you're muted.
Oh, thank you for that. Yeah, I'm sorry. Is the screen visible?
Yeah.
Yeah, okay, thank you. Yeah, so guys, now we'll be implementing the polynomial regression. So we are importing the necessary libraries. We are importing NumPy as NP. We are importing matplotlib as PLT, and we are importing sklearn, right? So sklearn, it stands for scikit-learn. It is a machine learning library in Python. It's widely used for tasks like data analysis, because of the simple tools it offers. So we are importing the linear regression model from sklearn, right? And from sklearn.preprocessing, we are importing polynomial features. Now, polynomial features is a class that is used to generate a new feature matrix. So it will be containing all the possible combinations of features up to a specified degree. Right, I'll be showing you like where we are specifying the degree and that. So suppose you specify degree equals to 3, then you will have the combinations of h square and h cube, right? All the orders till the specified degree, right? So first, we are generating a random 2D array. So we are generating the h values. So np.random.rand gives you some values between 0 and 1. So 6 times that value, right? When you do that, you get a value between 0 and 6. And subtracting 3, it gives you a value between -3 and 3, right? So you are basically generating a random 2D array with h values from -3 to 3, right? Why are you generating a random 2D array? Because for most of the imports that we like most of the models that we import from sklearn, we require 2D arrays. So we are generating the y value for a specific curve. So now we are like, we need some data set, right? So we are actually creating the data set over here. So we are specifying the polynomial as 2 plus 3h minus 4h square plus half its cube and plus np.random.random 100,1. So basically here we are adding noise to the y values generated, right? Now poly features is equal to polynomial features degree equal to 3. So here we are specifying the degree, right? So we are like, okay, we are implementing a cubic polynomial of degree 3. Now here we are given include bias equals to false. So bias was the constant term, if you remember, right, in the polynomial regression. Why are we giving include bias equals to false? Because we are already implementing the polynomial regression on the linear regression model, right? So the linear regression model already has a bias term. So you don't necessarily need to include bias again in the polynomial because it's already included in the linear regression model over which you are importing the polynomial features, right? So h poly equal to poly features dot fit transform. So this transformer, it converts the input features to polynomial features, right? So you have specified the degree equal to 3. So you will be getting the combinations h square and h cube. Now, yeah, so here you are initializing your linear regression model. So so here you are fitting the curve to the data set, right? So W0 is the coefficient of h, is the bias term, the constant term. W1 is the coefficient of h, W2 is the coefficient of h square, and W3 is the coefficient of h cube. Right. So basically what you're doing over here is you have generated a data set and you're trying to fit a curve to that data set. So it looks like this. Now this is obvious because we are ourselves fixing the h values and we are hard coding the polynomial. The only things we have added noise, and obviously this curve is going to closely fit this data set, right? Now, now this is how we implement polynomial regression model. Now let's look at bias variance trade-off. Right. So here again, you're importing numpy as np and matplotlib as plt. So here you are setting the seed to 0. Now, as explained earlier by Anish, -3, 3, 20, and you have plotted the data set. Now this is how your data set looks like. Now to this data set, let's try fitting a straight line, right? So what we are doing here is we have initialized the model as linear regression. We are trying to fit a straight line to this given data set, right? So when you try to fit a straight line to the given data set, this is how it looks, right? Now this is a clear case of underfitting because you can see that the straight line is not able to capture the patterns in the data, and it's clear case of underfitting. Now what we'll do is we'll try to add a new feature. We'll try to add a quadratic feature. Now, when you add a quadratic feature here, you can see that you're specifying the degree as 2, right? So basically, you're including all the combinations till degree 2, that is h and h squared. So now here you're trying to fit a quadratic model to this data set. Now, when you see that, okay, this curve looks fine, but again, it is not the best fit for this given data set, correct? Now, you obviously know what is the optimal order, right? Because you yourself generated the data set with a cubic polynomial. The order is 3. Now, when you try to fit a quadratic, it doesn't fit the best. Now, let's try including biquadratic feature. So when you specify degree equals to 4, what you get is you get all the combinations till degree 4, and this is how it looks. Now, this is where overfitting starts. The optimal degree, like the best fit curve, was a degree 3. Now here the degree is 4, so the overfitting has slowly started. Now, when you change the degree to 10, and I change the degree to 10, you can see that now the curve, the plot is trying to pass through almost all the points. So yeah, now this is also a case of overfitting. Now, what happens when you increase the power something like crazy like 25? So yeah, so the model, it has learned the training data set very well, right? So it's trying to fit the training data the best. It's trying to pass through all the points, but it is most likely to perform poor on the testing data. Because see, if there is a small fluctuation in the training data itself, the output is the predicted value by the model is going to vary by a lot, right? Vary by a lot, big magnitude. So even if you change the training data slightly, and if you get an entirely different function, then what is the point of the model, right? So the model becomes useless. So this is a classic example of overfitting. So guys, any doubt till what we have discussed till now? Okay, so yeah, so this is with my part. So I'll be concluding my part over here. Now Anish will be taking logistic regression. Guys, please hold on for a second. Guys, yeah, some of you are telling that you couldn't scan the attendance QR. I'll be displaying it again, so don't worry.
Hey guys, so there was a technical issue. Please wait for 2 minutes. We'll be back. The content.
Yeah, so I clarified the doubts from the chat. So yeah, for the example given, 3 was the best fit. How was 4 higher than the cost function? No, the thing is, see, we created the data set, right? The data set we created was of cubic order. So when we tried to fit a degree 4 model, what happened was like it was the overfitting. It was a case of overfitting. 3 was the best fit. Yeah, you are right. So when you try to fit a polynomial of degree 4, it's a clear case of overfitting because you are exceeding the optimal degree, right? So degree 3 is the optimal degree and 4 is a higher degree. So yeah, when you have a higher degree, you will have high variance. So yeah, it leads to overfitting. Yeah, so in those cases, what you do is you calculate the cost function and then you plot the cost functions for various degrees. And then the degree for which the cost function is minimum, that's going to be the optimal degree. I hope that doubt is clarified. Yeah, Anish, you can start.
Hello everyone, I hope I'm audible. Is there an echo?
Yeah,
No,
you're
you're
audible.
not.
There is no echo.
Okay, so we'll be starting with logistic regression. So logistic regression is, I'm sorry, I'll just start in a second. I'm getting an on my side. Sriram. Okay, I think, yeah, now it's fine, I'm assuming. So yeah, let's start with logistic regression. So logistic regression is slightly different from the other two models that we saw. We'll see in what manner it is different. So basically in supervised machine learning, we use it for two main tasks. One is regression and one is classification. Regression is used to predict continuous numerical values, while classification is used to predict categorical labels. So till now, whatever we've been doing with linear regression and polynomial regression, we've been predicting continuous numerical values. Like we predicted the house price. Similarly, it can be used to predict the stock market prices and a lot of other things. However, now what we're going to be doing is classification. Classification again is used to predict categorical labels. So what does this mean? Basically, we'll be classifying things into different types. Let's say you get a lot of emails, some of them is spam. You classify them into spam and not spam. That is classification. And it's used in like, there are a lot of use cases. Let's say you have like a lot of reviews for a restaurant. You can filter them into positive, negative. It's called sentiment analysis. And yeah, so logistic regression is basically used for classification. So then the question comes, why not call it logistic classification? It's used for classification, right? So the answer to this lies in the math of logistic regression. Logistic regression is nothing but the output of a linear regression put into a special function called sigmoid function. So what we do is, in linear regression, we have the formula wx plus b. We pass it through a sigmoid function. And now the sigmoid function basically has a range of 0 to 1. And this helps us predict the classes better. We'll see how this happens. Let me just read out this slide. In linear regression, our main aim is to estimate the values of y-intercept and weights, minimize the cost function, and predict the output variable y. In logistic regression, we perform the exact same thing, but with one small addition. We pass the result through a special function known as the sigmoid function to predict the output y. So this is the sigmoid function basically. So in sigmoid function, you can see like the main thing is it has a domain of -infinity to +infinity. So we can just feed the output of a linear regression to it. Meanwhile, its range, however, is just between 0 to 1. So you know what else is between 0 to 1? Probability. So that's exactly what we are finding here. Let's say like there are two classes, one is 0 and one is 1. The output that we get from a logistic function is the probability that the class is 1. So we'll get to that later. For now, let's just understand sigmoid function properly. So as I said earlier, the domain is -infinity to +infinity. And then the range is 0 to 1. And this is really helpful for us. Another really important concept when it comes to logistic regression is a decision boundary. Decision boundary basically separates like the values which are present in different classes. What does this mean? Like, for example, you can see a circle here, right? So the dots within it is not obese, while the dots outside the circle are obese. So this circle separates the values from each other. So this is the decision boundary. It can be in various shapes. For example, here it's like it's a slanting line. It separates classes with y is equal to 1 and y is equal to 0. So till now, I mean, I will just discuss stuff in which you have two classes, mainly 0 to 1, or in this case, obese or not obese. What happens if there are three classes? So when there are more classes, the decision boundary is not just a straight line or a single line anymore. You can see here the decision boundary for logistic regression in the iris dataset. You might have come across iris dataset in yesterday's session. It contains like three output classes. It's three types of flowers basically. So the decision boundary for that looks something like this when we apply a logistic regression. And of course, for multiple classes, it's a bit more complicated. We'll get to that in a while. So I hope you've understood decision boundary. It's basically to separate different classes. So now it comes like, why do we need a logistic regression? Like, of course, it's for classifying, but why can't we just use a linear regression as a decision boundary? So we'll get to that. So it's the same data set. It's a hypothetical data set. And we've basically used two models. One is linear regression and one is logistic regression. So the main differences are the logistic regression has a range of 0 to 1, as I've said repeatedly. So because of this, the curve kind of fits within the data points. However, in linear regression, it exceeds 1 and it goes below 0 also at some points. For example, at x is equal to 0, y is going to be negative. And at x is equal to this point, y is going to be greater than 1. And one more thing, let's say that you're going to use this linear regression as a decision boundary. You can see that roughly half the points are towards the left and half the points are towards the right. So, you know, if you get half the answers right, it's basically an accuracy of 50%. And you can get an accuracy of 50% by just randomly guessing values. You don't need a model for that. So what happens in logistic regression is, as I said earlier, the output is the probability of the value being 1. So at the point where y is equal to 0.5, we'll form a decision boundary. So there'll be a vertical line passing to the place where my cursor is moving. Anything to the left will be 0 and anything to the right will be 1. So yeah, of course, if you see clearly, there's going to be like 1 or 2 points which are going to be predicted wrong. But then the accuracy is pretty good. So like you may ask, why not do the same thing over here? Well, the thing is, the output of a linear regression isn't really probability. You can see this clearly because it goes more than 1 and less than 0 at some points, which doesn't make sense when it comes to probability. So like this, I mean, this is the same thing that we saw in the previous slide, except with a more relatable example maybe. So basically at any age before 18, you can't vote, right? And at some ages above, I mean, every age after 18, you can vote. So that's what this data represents. We'll be applying a linear regression to this. So this is the linear regression. So like one thing you see is assuming y is equal to 0.5, we have formed a decision boundary at the middle. Like, of course, this is not right because the linear regression isn't really the probability. The problem in this is if you add a new data point, let's say we add something at 17 or 17 and a half or something, it will still predict it as can vote rather than can't vote. However, if this was a logistic regression, then the graph would adjust in such a way to accommodate the new data sets as can't vote. So basically, you'll get a higher accuracy. We'll see more about this during the code implementation. So let's get into the math. So you saw the cost function and gradient descent and all that in linear regression. Let's see how it's different for logistic regression. So this is the cost function of linear regression. You might remember it. Sriram explained it just few minutes back, maybe. So cost function is 1 by 2m sigma fwb xi minus yi whole square. This term is nothing but wx plus v. It's just written in a more complicated way. Meanwhile, yeah, it's given here fwb xi is equal to wxi plus v. And like I've been repeatedly saying over the past few minutes, logistic regression is nothing but linear regression with a sigmoid function. So this is the modified function for logistic regression. So now the question comes, like, can I just directly put this into the cost function? Will that make it like, will that work? Do I need to make some more changes before I go on to gradient descent, or will this cost function be working? So like before I answer it, you guys can scan the Slido and try answering it, and then we'll get to the discussion and leave this on for a couple of minutes. So let's see what you all have answered, and see quite a few participants over here. So the highest votes are for yes. Okay, let me just read out the question. Can we use the same cost function for logistic regression as linear regression by simply replacing wx plus b with sigmoid wx plus b, where sigma is the sigmoid function? Okay, so I've gotten maximum votes for yes, because the sigmoid function ensures that the output is between 0 and 1, making it suitable for logistic regression. Okay, second most is no, because the mean squared error used in linear regression is not appropriate for the probabilistic outputs of logistic regression. The remaining two have lower amount of votes. Yeah, so I've gotten a good amount of responses. So I think I'll answer it. Well, the majority of you have actually gotten it wrong. We don't use the same cost function for linear regression and logistic regression. We'll get to why in the following slide. So basically, this is what happens when I just put in FWB into the cost function of linear regression. So when it's a linear regression, it's just Wx plus b. So that's a nice convex curve with one global minima. However, when I put the sigmoid, the function gets really complicated. Because of this, you get like a lot of local minimas and one global minima. And for gradient descent, you just start at any random point, right? So for linear regression, I start here and I reach the global minima. It's pretty easy. But then when it comes to like this case, there's a good chance that you'll get stuck up at a local minima. But that's not the point, right? We need to reach the global minima. And this is not really proving to be helpful for us. So like that's why, coming back to the poll, the correct answer is actually no, because the mean squared error used in linear regression is not appropriate for the probabilistic outputs of logistic regression. We have a special cost function for logistic regression. So this is the special cost function that we have for logistic regression. As you can see, it's different for y is equal to 1 and y is equal to 0. We will soon look at a case which is like convenient for all ranges of y, but for now, let's just look at this. Since we've taken log, it's kind of really smoothened right now. Now you can see both of them part of the same graph. So like, I mean, I don't know if it's very intuitive, but what we're going to do is we're going to add up both the graphs to get a neat cost function. We'll come to it in one of the next slides. Yeah, we'll come to it during optimization. So yeah, this is, I mean, it looks scary in starting, but then if you notice closely, it's just the sum of these two individual terms. You put y is equal to 1, this term cancels out. You put y is equal to 0, this term cancels out. So this is just the sum of that. One thing about logistic regression is you're not going to get directly 0 or 1. I mean, that'll happen very rarely. You'll probably get some probability, right? So it makes sense to use this than those initial graphs. And one more interesting observation is, here you can see it's not 1 by 2m. In linear regression, it was 1 by 2n because there was a square term. So when you do differentiation using chain rule, the 2 and 2 gets cancelled. But here there's no use of that. So we are essentially going to be doing the same thing that we did in linear regression. W is equal to W minus alpha, which is learning rate, into dj by dw. B is equal to B minus alpha, dou j by dou B. So I mean, like the differentiation for this is not really hard, but it's pretty lengthy. This is what you arrive at the last step. So you get dj dou j by dou w is equal to 1 by m sigma fwb minus y xj. Meanwhile, dj by db is equal to 1 by m. Same thing, but without the x. It's really similar to how it was in linear regression. There's always an extra x because it's wx. That's why when you differentiate with w, you get that extra x. And for b, b is alone, so you don't really get anything over there. So yeah, we are done with app optimization actually. So if you guys have any doubts, you can just put it in the chat. I'll read it and answer it. If not, we'll be moving on with multi-class regression. Just stop for a minute, maybe in case you're typing something out. I don't see any questions. So yeah, I can't see any questions on my screen at least. Like, how do I choose algorithm for different models? Well, like when it comes to logistic regression, see, one thing is like when if you're doing a hackathon or something, most of the cases you'll be opting for stuff which is more complicated than what you see over here. I mean, linear regression is rarely used in like high level regression problems. However, in this case, you can okay, I'll just go back to the previous slide and answer. Yeah, so in this case, you can see like logistic regression is like used for a completely different task. It's used for classification. So like one answer to that question can be like logistic regression is for classification, while the other two are for regression. And between linear and polynomial, it depends on the complexity of the data. I mean, in the polynomial regression code implementation, there's an option to choose the degree, right? So you can just play around with that and decide. Is classification only valued for functions only having two outputs? Well, till now, whatever I covered, yeah, it's two outputs. But in case you didn't see, the next slide was about multi-class classification. So we'll be heading to that. How much data should we feed for it to give accurate results? I mean, usually we do a training and test split of like 80-20, which means 80% is training data and 20% is test data. So heading to multi-class regression. So multi-class regression is used when the output has to be classified into more than two categories. So yeah, once again, coming back to the iris dataset, I mean, it's again, basically there are three flowers and you'll have to classify it into the correct flower. In this case, there are two feature columns and this is how the decision boundary is. We'll see how we arrived at this decision boundary. We'll be doing, we've been using sigmoid function till now. We'll be using a slightly similar, it's not really similar, but yeah, you can see it. We'll be using the softmax function, which is basically e to the power zi by sigma e to the power zi to find the probability rather than sigmoid function. The advantages of this is, I can be ranging to any number. So that's the advantage. Someone has asked, how do you tell you are on a local minima and not the global minima? I mean, when it comes to linear regression, the curve has only the global minima, right? So it's like that. And one more thing is when you're in the global minima, basically you'll get a higher accuracy. You can say it that way. Basically, we need to reach the lowest point, right? So coming back to this softmax, Yeah, so softmax, of course, is e to the power zi by sigma e power zi. Here we can see we have like m inputs and we have k outputs. So like the softmax the summation will have k terms in the denominator. Like this is also pretty like intuitive to understand. Basically, we are like dividing the e to the power. We're dividing the e to the power of e of one class with the power of e of all classes. Zi is nothing but wx plus b. B is not mentioned over here, but it is included. So yeah, softmax is also like pretty easy to implement. And of course, there are limitations with logistic regression. As I said earlier, like logistic, there are way more complicated models which are generally used. All these models that you learn today are like the elementary steps to getting there. So logistic regression assumes linearity between input features and the binary outcome. So like all features might not have a linear relationship. For example, predicting the likelihood of a customer making a purchase based on their age and income may not have a linear relationship. So in these cases, you will have to do stuff like neural network or random forest. Random forest regression. We'll come to this later. So this is an example of a neural network. So spoiler alert, I guess you'll be seeing this in future sessions. For now, we'll move on to the code implementation of logistic regression. Just a minute. I'm just like loading it. It's just taking time. Okay, guys, like unfortunately, due to time constraints, we won't be able to go through the code implementation of logistic regression since it's already time up. So I think we'll just like share the attendance QR once again, and then we'll close for the day. However, we'll be sharing the notebook to you so you can go through it and ask us any doubts if you have any. And we'll also be sharing the assignments with 5 questions. And of course, there'll be like 3 more questions posted on the day of the next session, which is on Monday. So I'll just share the attendance in a minute.
Thank you, guys. The session is over. If you want to mark your attendance, you can do that